Log on, tune in, find out. Another good idea from Cambridge.
Beginning of afternoon session, and it is my pleasure to introduce the first speaker, Alexey Sevastyanov, who will speak about algebraic group analogues of Slodowy slices and Poisson W-algebras.
Thank you. Since Jonathan gave an excellent introduction to W-algebras this morning, so I will start with his definition and using his notation. So that I will consider an assaulted triple in a complex simple algebra G. And as you remember, one can associate to this triple finitely generated W algebra. And we can do it, for instance, in the following way. Let's consider the grading by the action of H induced on G. And as in Jonathan's talk, I will assume for simplicity that the grading is even. And that's, again, a pedagogical assumption only. So then E is an element of G2. And one has to consider a parabolic subalgebra, P. And its near radical, which I will denote by N. That's more common notation. Jonathan used M twiddle, I think, for this N. So then E induces a character of N by the pairing with E. With the help of the killing form. And one has to define the W algebra as the algebra of U of n invariance in the quotient of U of G by the left ideal generated by the kernel of this character. Let me denote this character by chi. So, and this is the W algebra. So now I would like to discuss some related geometric issues, and I would like to consider a similar geometric construction in case of algebraic groups. So first of all, I would like to describe the corresponding quasi-classical version of this definition. So this is a kind of quantum Hamiltonian reduction. And at the classical level, one can describe the corresponding reduced space with the help of the coadjoint action. So if we consider the corresponding graded objects with respect to the grading that Jonathan introduced this morning, then, well, let's see. Well, there are different filtrations, right? There is a natural filtration coming from U of G, and there is the so-called Kazhdan filtration. So let's use the standard one. In principle, it's not important. This will give the same Poisson structure. But let's use the standard one. So then the associated graded of U of G is the symmetric algebra of G, which should be regarded as the algebra of regular functions on G star. Yeah, the grading is even. So then next, the associated graded U of n is the algebra of regular functions on the opposite nilpotent subalgebra. Right? So then what do we do here? So when we factorize over the kernel of this character, we geometrically consider a certain surface in G star described by the equations x equal to E paired with x, which can be interpreted in terms of the moment map for the action of the coadjoint action of the unipotent group N corresponding to Lie algebra N. So let's consider the restriction of the coadjoint action of G on G star to unipotent Lie group N. So then this action is still Hamiltonian, so it preserves the Kirillov-Kostin Poisson structure on G star. And this action has a moment map. So then I claim that the reduced Poisson manifold, which corresponds to this algebra in the quasi-classical limit, is the following one. So this is the reduced Poisson manifold, which corresponds to the value chi of the moment map. And the level surface itself is simply E plus P. So it's isomorphic to E plus P under the isomorphism induced by the killing form. So then it's stable under the action of N, and the quotient is exactly the quasi-classical version of this algebra, which is in fact can be identified with E plus the centralizer of F in G. So that the W algebra is identified quasi-classically with the algebra of regular functions on the centralizer of F. So this statement is actually a theorem which was proved by Constant in case of regular nilpotent E and by Gunn and Ginsburg in general case. So let me somehow label it. I will need it later. And that object in the right-hand side is called the Slodowy transversal slice. And actually, historically, these slices appeared even earlier. They were introduced by Slodowy in the study for the study of certain singularities of the adjoint quotient map. So that's another story, and I would like to remind it a little bit. So perhaps I can call it part one. So that was a collection of some facts on W algebras. And part two is some recollection of facts on the adjoint quotient map and its singularities. So let's consider the following map. So this is a well-known map. So this is a composition of the inclusion of, the opposite way, of course. Of the inclusion of the algebra of regular G invariant functions on G with the isomorphism, the Harishchandra isomorphism. So then the dual map is called the adjoint quotient map. So the dual map sends G to the quotient H over W. Let me denote this map by delta G. So the point is that the fibers of this map are singular, and the singularities correspond to irregular elements. So at regular points of G, there are no singularities. Now, it was actually a suggestion, I guess, perhaps made by Grothendieck, to study simple singularities using this adjoint quotient map. So, and actually, he suggested to consider certain transversal slices to adjoint orbits in G, and to restrict this map to those slices. So let S be a transversal slice to adjoint orbits in G, and let's restrict the adjoint quotient map to such a slice. Then one can prove that every fiber of this map is a normal surface, and it has singular locus of codimension at least 2. So in particular, if S has dimension rank plus 2, then the fibers can only have isolated singularities, and they correspond to subregular elements. So that's how Slodowy constructed all simple singularities of types A, D, and E. And for that purpose, he introduced those slices for subregular E. They give exactly simple singularities. So now I would like to discuss similar constructions for algebraic groups. So let me start with the geometric side. Let's forget for a while that Poisson geometry, and let's discuss the geometric side of the construction. So can we, first of all, describe somehow and construct somehow simple singularities using conjugation quotient map for algebraic groups? Well, the answer is yes. Let's consider the conjugation quotient map, which is defined in a similar way. So let G be complex simple algebraic group with the algebra G. Then, similarly to the case of Lie algebras, I can consider the map, which is the composition of the inclusion of G invariant regular functions into regular functions, and of the Harris-Chandra isomorphism. Here T is a maximal torus in G. So, and the dual map gives me some map which I denote by delta G capital from G into the quotient T over W. So, and the same statements hold for that map. I mean, the statements similar to the statements about the fibers of the adjoint quotient map. So, in particular, if we have a transversal slice to adjoint orbits, and if we do, sorry, to conjugacy classes now. And if we restrict the conjugation quotient map to such a slice, then the fibers may have certain singularities, and if the dimension of the fiber is equal to rank plus 2, then the only singularities are simple. So we have the same statement in case of algebraic groups. So now the point is that how to construct such slices. And in particular, I'm interested in also a generalization of that Poisson geometric construction. So my goal is basically to construct some W algebras associated to such slices. So here is the definition. So I have to give it more or less for scratch, then I will explain my motivation. So first of all, let's fix some initial data. Let let P be a parabolic subalgebra. Now that's at the moment that's an arbitrary parabolic subalgebra in G. So let's denote by N its nil radical. And let's pick up an element of the while group. Well, perhaps I have to denote it by C to distinguish it from the slice. So then I will need actually not C itself, but I will need a representative on C in G, which I denote by the same letter. So the action of C on the maximal torus is given by conjugation by C. So I will also need the Lvy factor of P. And the corresponding subgroups, which I denote by P capital, N capital, and L capital, the subgroups in G capital, which correspond to these subalgebras.
The C's in T are just in T.
Oh, T was a maximal torus.
I see. Oh, no. Oh, yes.
Representative
Of C.
C is the normal.
Well, I use just the same notation for.
Okay.
Well, I just pick up a representative. Okay, so then I'm going to define some transversal slices to conjugacy classes in terms of that data. So, and for that purpose, I need to consider the centralizer of S in L. And I need to, C, sorry. Yes, I guess I will always make the same mistake throughout this talk, because C is more common notation for elements of the while group.
So this is ZL of C?
The L of C, yes. So please forgive me, I will always make this mistake, I guess. So, and I need a certain subgroup NS in NC. Well, as I
You
said,
can write that S
it's a kind of
to C.
S is equal to C. Is not equal to that S capital. Certain subgroup in N, which consists of the elements transformed by the conjugation by C into the say into the opposite parabolic. So, and finally, let's consider the following subvariety of G. And C times Z times C to the power minus 1. Well, the claim is that if roughly the action of C on N has no fixed points, then this is a transversal slice to conjugacy classes in G. So more precise statement said that if for any G or any N from N capital, there exists positive K such that S to the power K and S to the power C, well, again, is not an element of P. And the same fact is true for the opposite unipotent and parabolic. Then we have constructed a transversal slice to the set of conjugacy classes.
But transversal slice means so it's just intersections are transversal.
Yes, yes,
So
it's very weak
middle of
condition.
intersections is a point.
No, no, not necessarily, no. Well, for instance, if you consider subregular elements and transversal slices of dimension rank +2, then they are, so to say, in your sense, exactly transversal at subregular points. And all the other points, they are just
But
the dimension of
there
the,
will be a point to which it intersects transversally and in single point or something.
you mean exactly transversally. The dimension is, so to say, minimal.
Yes.
Possible. Well, at this point, I still don't know. I will give you some description, several examples when it's true. So, and that's just a half of the geometric story, because you remember we have another important geometric fact related to the slices, namely this one, the cross-section theorem, which states that this quotient must be isomorphic to the slice. So, but in order to somehow formulate this statement, I need something like
A priori, there's no relation between C and P.
no. Well, here,
bizarre.
yes, here we have a relation.
That's
Here we have a
right.
condition.
But nevertheless, I mean,
But I mean, the statement is still very weak.
it's not really.
So you claim that you can choose element in the white group such that
No.
No,
If
it's not
this
something,
is
it's just
true,
picking-
no, that's very general statement. I will discuss later how to pick up. in
this
certain
was my
cases.
question. You can always pick up.
Not always.
Not all.
Not always. Well, I will tell you how to do it in case of classical algebras and.
I mean, if P was the Borel, then would you make a specific choice of C or?
I will tell you. I will give you several examples, but still there is no general theory here at the moment. That's somehow difficult to associate to any element of the Weil group, parabolic subgroup or parabolic subalgebra.
Yeah, you think should be a link between C and
Yes,
P.
yes. Well, I will tell. Actually, I will give several examples which arise from the Kazhdan-Lustig map when you can associate an element of the Weil group to an nilpotent element. Then you can associate parabolic which simply comes from the nilpotent element. So, well, the Kazhdan-Lustyk map is still poorly understood. So it's well understood in the case of classical algebras, and then it works. And it works in certain other cases, for instance, in the case of subregular nilpotents. So I still don't know how to do it in general. Okay, so, but let me go to this statement without any specification of C and B. So, what can we consider instead of this level surface in case of algebraic groups? Maybe I have to, well, I don't know. Yeah, later. So I would like to finish with geometry, and then I will discuss Poisson geometry. So it turns out that instead of this level surface, in case of algebraic groups, one has to consider the following subvariety of G. N C to the power minus 1 times n. Well, why is it so? It's just because one can prove the following proposition, for instance. Oh, sorry, I missed that here. Well, under the same conditions as in the previous proposition, the conjugation action map is an isomorphism of varieties. So now examples. So the first, historically, the first example which was known since I think 1965 is due to Robert Steinberg. He considered, he studied the cross section to the conjugacy classes of regular elements in G. And he proved that if G is simply connected and simply connected, then in case when P is a Borel, and C is a Coxeter element, that is the product of simple reflections. So, I mean, we have to pick a representative in the while group of the pair G, B. So the positive roots are chosen with respect to this B. So then, the variety n c times c to the power minus 1 is in fact not only a transversal slice, but that's a global cross-section to the set of conjugacy classes of regular elements in G. That's one example. Example 2. And, well,
What's the C looking like? N sub C is
And sub C is, it's related to the positive roots which become negative under the action
I
of.
know that, but how many roots does it have?
Oh,
Exactly.
the dimension is equal to the rank, of course.
Exactly, and those roots are, it doesn't, their roots depend on the choice of Coxeter elements.
Oh, yes. But for any C, you will get a transversal slice.
But you don't have eigenvalues corresponding to those roots which have anything to do with generalized exponents.
What do you mean by eigenvalues?
So in Constant's business, you have G upper F, where you wrote it up at some point,
Yes.
right? And the eigenvalues of G upper F correspond to the generalized to the exponents.
Yes.
But here
Here there is nothing like that.
there is nothing like that.
No.
So, I mean, why does it work? I mean, somehow there's something which puzzles me now. This is,
Well, here
it's
the
got the right dimension. That's clear. I mean, right. So,
Here the problem is that, well, the situation of algebraic groups is in some sense worse. You have no gradings like in case of the algebras. And that's not only the point where the gradings are lost. For instance, if you compare the conjugation quotient map and the adjoint quotient map, then in case of adjoint quotient map, there is a nice homotopy which helps you to pull any fiber of the conjugation of the coadjoint action quotient map to small neighborhood of 0. So you just rescale all generators of Lie algebra, and you can choose always homogeneous J-invariant polynomials. So your rescaling pulls any fiber to a small neighborhood of 0. There is nothing like that in case of algebraic groups. So the fibers of the conjugation quotient map may look quite tricky away from the identity, the maximal torus. And here also there is no good grading. So these, the functions on this NC, the regular functions on these slides, they are generated by the characters of fundamental representations of G capital. But that's all what one can say.
So you in the classical case we fix the nilpotent element.
Yes.
And so is there any unipotent element of G floating around here, or this is somewhat different approach?
Just a moment. Well, I'm just describing some examples. No, in general, no. The answer is no. But I'm going to discuss several examples when you associate your S, your C, to an important element by means of Kazhdan-Lustig map. So in fact, well,
so one of the things you have to prove here is that you never hit 2 points of this variety
Yes.
in any given.
yeah, that's a global cross section.
Yeah.
Here the picture is local. All these transversal slices are local, just locally transversal. But this statement is global, and simply connectedness is very important. Because, well, that's basically because in this case the characters of fundamental representations generate the algebra of all regular functions. Okay, so second example. In the second example, I will use the Kazhdan-Lustig map, which I'm not going to describe in detail. That's a certain map from the conjugacy classes of unipotent elements in the Lie algebra G to conjugacy classes in the Weil group. Ready? So it sends nilpotent orbits in G to conjugacy classes in W. in case of SLN, for instance, nilpotent elements and conjugacy classes in W are parameterized by partitions of N. And the Kazhdan-Lustig map simply sends a nilpotent orbit which corresponds to a given partition to the element of the Weyl group which corresponds to the same partition. So at the same time, you know that to a given nilpotent element, one can associate a parabolic subalgebra using the grading arising from that SL to triple, which I fixed in the beginning. And in fact, the point is that one can choose a representative in the corresponding conjugacy class in W in such a way that this condition is satisfied. I will tell you how to do it.
But can you choose other guys when that condition is satisfied?
Well,
It's
that's
nothing to do with Kazhdan-Lustig image.
well for in case of SLN.
Well, no, I don't know. Maybe not.
I don't know. That's just a natural choice how to associate.
You've got one choice which comes from Kazhdan-Lustig, but you have other things that also.
Yes. I don't have the complete picture. I don't know. So if there is any, then one should be able to associate an element of the Weyl group parabolic subalgebra somehow. So I still don't know how to do that. So, but well, in this example, given this nilpotent in terms of blocks of dimension d1, dr, one can describe C in terms of the fundamental representation. So, namely, if we pick up vectors generating if we split the fundamental representations with respect to the action of the SL to triple, then one can pick up the generating vectors v1, vr, such that e to the power I vj generates a fundamental representation for j from 1 to r, and I from 0 to d j minus 1. And e to the power dj annihilates vj. Then the corresponding element c sends e to the power I vj to, let me double check the signs here. To e to the power I minus 1 vj for I greater than 0, and it sends v to the power vi to minus 1 to the power vj minus 1 e to the power.
So it should be 2 dj minus 1 everywhere?
Sorry?
Twice dj, isn't it?
vj.
No, I mean dj minus 1. Shouldn't it be 2 times dj minus?
No.
These are
No, the standard is not adjoint.
No, it's not adjoint, it's fundamental representation.
Okay.
It's fundamental representation. Okay, so let me finish dj minus 1 vj. So, and with this C and with parabolic arising from that SL to triple, this statement works. And one can do it for all the classical Lie algebras. So, in case of all classical Lie algebras, we have description of Kazhdan-Lustig map in terms of partitions. One can do that.
For all
Oh, yes.
Well, what do you need the sign for? You really need a sign there?
Well, the sign is here.
You really need that?
Yes, yes. Well, because C must belong to SLN. So yes, otherwise,
But you said
if you don't fix it, the determinant could be equal to -1. Okay, so perhaps I'll use the last example here, which is related to simple singularities. Well, in case of subregular E, the Cardan-Lustig map is also known. So, and one can associate again an element of W with the help of the Cardan-Lustig map. For instance, in case of SLN, one has to take the following C as, well, if E is, for instance, E alpha 1 plus and so on, plus E alpha L minus 1 plus E alpha L plus alpha L plus 1 plus E alpha L plus 2 plus and so on, plus, well, the last E alpha, say R. Then C is the product of the corresponding simple reflections, of the corresponding reflections. So that root is not C.
It's a regular in SLN.
Or SL, well, n minus 1. Okay, so then actually that's a consequence of that statement that the machinery works. But one can do it not only in case of classical algebras, one can do it also in case of all exceptional algebras to obtain all simple singularities.
What is
L, that's just an arbitrary number which is less than n minus 1.
so there are different
So one root is not simple, one root vector is not simple.
so there are different choices.
Yeah, there are different choices. Of course, they are all conjugate to each other because there is just one conjugacy class of subregular nilpotent elements. Okay, so I think that's enough. Anyway, I have no time for more examples. Now let's discuss the Poisson geometry. So let's switch to Poisson geometry. So I would like to equip my transversal slices.
what is the dimension of n of C in the subregular?
In this case, in case of SLN, the dimension of MC is equal to rank plus 1. But there is also part arising in the transversal slice arising from the centralizer, which has dimension 1. But that's, in case of subregular element, that's a kind of exceptional case, because in case of all the other simple algebras, there is no centralizer part.
So you have right dimension only
Yes.
in SLN.
No. The dimension is always right. I mean, there will be no this part in the transversal slice.
There will be in type B.
Oh.
It's not distinguished in type B, I think.
They are not distinguished. Even if they are not, maybe there are some simple elements, but they are not there. So the point is that in all the other, in case of all the other series, these elements are products of rank plus 2, of rank reflections with respect to linearly independent roots. So that's why even in the Cartan subalgebra there is no fixed vector. Not only in the sublattice generated by positive roots. So ANC. Yes, that's here. That's n minus. Right, and the dimension of Z is 1. So the dimension of the slice is correct. Okay, so now let's go to Poisson geometry. So I would like to equip my slices with some Poisson structures. So first of all, can I do some similar trick to the trick with Kirillov constant Poisson structure and the coadjoint action? Can I make the conjugation action compatible with some Poisson structures in some sense? Well, the answer is yes, but the answer is tricky. One has to go to the theory of Poisson Lie groups, where the dressing action becomes conjugation action in case of simple algebraic groups. And one has to equip G with certain Poisson Lie group structures. So let's equip G with the quasi-triangular Poisson Lie group structure. So it means that G is a, well, that's a Lie group, that's a Poisson manifold, and multiplication is a Poisson map from the product G times G into G. So then, in fact, I will need not only this Poisson Lie group, but I will also need the so-called dual Poisson Lie group.
So is it important which quasi-triangular Poisson structure you
Yes,
use?
it's very important because I have to, well, I don't fix it at the moment, but I need to equip these particular slices with Poisson structures. So, and I would like to do it using Poisson reduction somehow. And in the reduction procedure, there are certain restrictions arising from the fact that this will be Poisson manifold, and this somehow restricts the corresponding quasi-triangular structure. Okay, so I think I don't have enough time to go in details with Poisson Lie groups. So roughly, the group G star is constructed in the following way. First, we consider the tangent Lie by algebra to G. How do we obtain it? We linearize the Poisson structure as the identity of the group. This gives you a commutator on the dual space to the Lie algebra of G. So we have Lie algebra structures on both G and G star. And in addition to that, we have a certain compatibility condition which arising from the fact that multiplication G is a Poisson map. So then the notion of this compatibility condition is symmetric with respect to G and G star. And one can consider another bialgebra, G star G. And to this bialgebra, one can associate another Poisson Lie group, which, for instance, well, one can always associate simply connected Poisson Lie group. So as a Lie group, it's reconstructed using Lie theorem, and then one can integrate the Lie commutator on G to Poisson structure on G star. So then there is a realization of G star in terms of G as a Poisson manifold. There is a nice realization. Actually, one can realize G as a dense open subset. One can realize G star as a dense open subset in G. Well, I can even write down the formulas for Poisson brackets on G and G star in terms of left and right in my invariant vector fields. So this is the Poisson Lie group structure on G. So nublas here are right invariant derivatives. They are elements of G star, which we identified as G by means of the Killing form. And R is a linear operator on G, which is called the classical R matrix. It satisfies a certain equation, which ensures that the Jacobi identity holds. This equation is called the classical Young-Baxter equation.
It's Poisson bracket for functions on G.
Yes, on G.
Are you assuming that G has that the R plus R over that G has a non-degenerate form?
Yes, it's complex semi-simple. It's still, we are still in the same position.
Okay.
I never left my framework. So, and classical R matrix. So then, in terms of, well, I can even write down the Young-Baxter equation. So then one can realize G star as a Poisson submanifold in G. Moreover, G star will be an open dense.
R is endomorphism.
Yes. R is an endomorphism of G. And R is symmetric with respect to the Killing form. So then, for completeness, I will also write down the Poisson bracket on G star, realized as a Poisson submanifold in G. Well, anyway, it's open dense. So I can actually extend it to G. By brackets, I denote the Killing form. So that's maybe not very informative. I just do it for completeness. For us, the only important fact is that if we consider Poisson Lie group G and Poisson Lie group G star realized in G, then the conjugation map is a Poisson, the conjugation action is a Poisson mapping. So, and that's primarily important for us.
But is this G star is invariant under conjugation?
Well, I mean, it's open dense in G. I can extend my...
It's a rational action.
I can extend, well, for simplicity, let me extend this Poisson structure to G. So basically...
Then it will going to have poles, yes?
This action,
No, this Poisson structure.
the bracket or what?
Yeah.
No. These are the gradients with respect to the G group structure, not G star. So I describe everything in terms of G. So I don't need actually G star group structure, which looks more tricky in this realization.
So G star is not closed under conjugation, but
Yeah. It's generally it's not. Okay, so now, now remember that in case of Lie algebras, we first restricted the coadjoint action to nilpotent subalgebra. And in case of Lie algebras, it was a kind of automatic that this restriction is still a Hamiltonian group action. In case of Poisson Lie group actions, that's not true. You cannot always restrict your action to subgroups. And I need here to restrict my action to N, a unipotent subgroup. But what I need from this restriction? Let's recall the cross-section theorem, which I already erased. So somehow I would like to make this restriction compatible with this cross-section theorem. And as I said, this submanifold, this subvariety will play the role of the level surface of the moment map. And the cross-section itself will be a subvariety in G star over N. So first of all, I have to take care if this quotient is a Poisson manifold. So, and this imposes a restriction on the bialgebra structure.
So in this formulas you have replaced the delta prime.
Delta. So these are the derivatives with respect to right invariant vector fields, and those are the derivatives with respect to the left invariant vector fields. Okay, so now the claim is that G star over N is a Poisson manifold if the following condition is satisfied. The condition will be formulated in terms of R. Let's consider the following operators, R plus minus 1/2, R plus minus identity. Then, in fact, the images of these operators are some subalgebras which are almost parabolic. So for any classical R matrix on a complex simple Lie algebra, these images are almost parabolic, roughly up to some Cartan factor. So more precisely, they are contained in some parabolic. Well, maybe I have to denote them somehow by different letters. And
Are they unimodular?
these parabolic.
No, the B plus minus.
B plus minus. They are roughly parabolic up to some Cartan factor.
Yeah, I'm just wondering if that makes it unimodular.
I don't know. So then these parabolics have some nil radicals, which I denote by n plus minus. And then the condition says that n, the algebra of n capital here, must be contained in n plus. Under this condition, G star over n is a Poisson manifold. So that's just the half of the story, because now we have to ensure that the slice is a Poisson submanifold here in this quotient. And this gives rise to other list of conditions which are more tricky. And in order to describe them, I have to go into the Belair-Drinfeld classification theory of classical R matrices.
So sometimes the standard structure doesn't exist that satisfies the condition. The non-standard exists.
Yes, non-standard exists, yes. For instance, in case of all subregulars, one has to take some non-standard structures. Well, I think I have to stop here. My time is over. So. Well, I can write down, by the way, for the case of subregular, if you are interested in those R matrices, I can write down.
Yes, please.
So, in case, for instance, of subregular nilpotent in SLN, in case of SLN.
Is it not possible that you could have that thing there being a Poisson submanifold of the Poisson subspace without the intermediate
Here?
that you've just proved? Yeah. You might have that thing with your left, where your left finger is being a Poisson space, without the
It could be not.
your right finger is being.
Yes, it could be not a Poisson submanifold. This gives actually the condition that this is a Poisson manifold, and here it's much more restrictive.
Which is that could be a Poisson manifold in the big space without that.
Yeah, the quotient G star over N is easy to make a Poisson manifold.
Doesn't matter.
Yes, but the other inclusion is more tricky. So, okay, in case of C subregular, E subregular in SLN, our matrix is P.
Maybe you can draw a picture of the Belair-Drinfeld triple. It's more.
Yes, I mean, in this case, the only non-trivial part which is different from the standard one acts on the Cartan subalgebra.
Ah, okay.
The root data is trivial.
Okay, okay.
So this will be P, how to denote it? Say M minus P M bar plus 1 plus C over 1 minus C. So here M is maximal nilpotent containing my N. So then P z orthogonal is the orthogonal projection operator onto the orthogonal complement to the centralizer of S in the Cartan. And on that part, 1 minus C is invertible, and one has to add this extra piece. Actually, the structure is the same for all subregular nilpotents. The bialgebra structure is the same.
He sees the Cox.
But Z is 0 for all the other series.
So that he sees the Cox terrain?
No, here C is, well, that's the element which is associated to a subregular. That's the subregular case.
But then 1 minus C is not involved.
Well, in case of Coxeter, so you're interested in the Coxeter case, then here we have to put the projection operator onto the Cartan subalgebra. C is invertible. It acts without fixed points on the Cartan subalgebra.
No, but I'm saying if C is not Coxeter, then 1 minus C is not.
Oh, yes. That's why I put this projection operator. I project it out.
Then it's invertible.
Yes, then it becomes invertible.
What about the subregular cases for others?
Well, as I said, it works. The same formula holds.
But there is no root data, only a Cartan.
Yes, there is no root data, hopefully.
But sometimes you need the root data as well.
I think so. I haven't investigated it in details, yes. But I'm sure that's not enough.
And have you tried to use the setting of quasi-Poisson reduction of Alexeyev, Malkin, and Mayanerian?
No.
Because then you may not need, the conditions might be less restrictive in that case.
Oh, that's quite natural condition. That condition actually said you that it's equivalent to the fact that the dual of n is a subalgebra in the dual of G star, or in the dual of G. That's more or less sufficient and necessary.
Any other questions? Actually, I have last one. Have you tried to quantize?
Oh, that's extremely difficult. Yes.
Okay.
I don't know. One probably must have some general setting for quantizing constraint reduction. I mean, Poisson reduction to do that. Well, I did it in case of Coxeter C in my PhD thesis, but it was 10 years ago. And in that case, you can write in explicitly everything in terms of generators and relations in the quantum groups. So then,
So that's, we look at Q2.
yes.
Do you get any nilpotent leaves? Symplectic leaves, so you get this Poisson manifold.
Yes. And it? Oh, wow.
You have and the important ones, the ones which contain things.
I don't know how.
There is no, is there a
I
fixed
don't-
water?
Fixed point. What?
There is no C star action on this.
There is no system.
So there is no fixed point.
Maybe there is a special point corresponding to the origin. Yes.
I don't even know.
Is there any
Otherwise-
distinguished point?
Well, perhaps that's c to the power minus 1 itself.
And is the Poisson
But-
bracket 0 at that point?
Well, I have some examples, but as you said, there is no C star action.
I mean, if it is supposed to be a trigonometrization of Slodowy slices, then there should be, at least at the formal level, it should be the same. So there should be a point.
Perhaps,
Such that
but
in the formal neighborhood of that point, you didn't do anything.
well, perhaps, but you see that C is it's quite far from zero, from the identity. Sorry.
But there should be a theorem that the formal completion at that point is
Perhaps.
the same as in
Yes,
the
formal
line
completion,
case.
yes. Perhaps, yes. But if you consider regular algebras, Poisson algebras of regular functions, they are quite different.
Because, for example, for quasi-triangular Poisson Lie group, not necessarily.
Yes, formal
There
completion.
is formal completion.
We can expect that they are the same.
So let's thank the speaker.